Hello, everyone. Welcome to our sixth edition of eMissions Talks webinar series hosted by Process Ecology. Today, we will be talking about the A to Z of tank emissions, covering everything from quantification to mitigation. For this session, we will not be sharing any slides, so this will be more of a conversational format. I will introduce here Alberto and Dennis, and they will go over their insights. So please feel free to submit your questions. There's a Q&A box available throughout the presentations. So yeah, we will get to these questions at the end of the session. So we just need to change the viewing of this because it's not quite. Okay, here's Alberto. Welcome. And here's Dennis. Thank you for joining us today.
All right. Thank you. Good afternoon, everyone, and thank you for joining us for this webinar today. My name is Alberto Alba. I'm the CEO here at Process Ecology. Like Sophia mentioned, we're going to have a bit of a conversation here between me and my colleague Dennis Westphalen on our perspectives around tank emissions. Before that, just a super brief introduction. Myself, well, I've been, for the past 30 years working in process modeling, optimization, and more specifically in the area of air emissions for oil and gas for a good 20 years. And really, my journey started. I did my undergrad in Mexico City. Then I went to the UK, to the University of Manchester for my PhD. And there I really got engaged in everything around modeling and simulation. When after graduation, then I had the opportunity to come to Calgary to work for Hyprotech, that company that developed HYSYS, which is the kind of global leader in process simulation for oil and gas. After that, I continued with my activities in process simulation and optimization with the CanMed Group, Natural Resources Canada. And then after that, with Process Ecology, a company we founded 2005. That's many years ago. Anyhow, here with me is my colleague Dennis Westphalen. He brings a wealth of knowledge in this topic. So Dennis, would you mind sharing a few notes on your background?
Yeah, sure. Hello, everyone. I'm Dennis Westphalen. I lead the engineering services here at Process Ecology. And I also come from South America, actually. I'm from Brazil, was born, grew up in Brazil, did my studies in Brazil. And actually, Alberto, I don't know if you remember, we met for the first time in Brazil. Do you remember that?
Yeah, no, that's a great story. That's a great story because I think it was 1996, and I was still working on my PhD. And then me and a few colleagues, we were sent from the University of Manchester to teach process optimization courses in Brazil. And then, who was sitting there in the classroom but a young Dennis. And who knew we were going to be working together.
That's right. Yeah, but anyway, so at the time I was working on my PhD down in Brazil. And then I had connections with Petrobras, which organized the event, and that's where we met in Rio. After I finished my PhD, I also moved to Canada, and here we meet again at Hyprotech. So we work together at the Hyprotech. Then we parted ways, worked a little bit on the engineering office at Jacobs Consultancy at the time, worked with a few operators, Nex and Sinox and Core, and then finally I'm back to working with Alberto and the other founders. We work together back at Hyprotech and AspenTech. Anyway, so looks like we're talking about methane emissions. And Alberto, why don't you start telling us why do we have to worry about methane emissions?
Well, that's a great question. But look, I'm guessing everybody in the audience knows this. Of course, methane, a strong climate forcer has been identified as 28, and the number keeps changing depending on the time and all these things. But a big climate forcer, there's consensus around the world about this fact. And what that led is, governments all over the world, especially with oil and gas operations, to start developing regulations, implementing regulations to minimize the emissions of methane to the atmosphere. Again, particularly from the oil and gas sector. So today, many of you in the audience will know this, and it's probably you're facing that day to day. The oil and gas operators here in Western Canada, they're facing several regulation and requirements for reporting reductions around methane emissions. Particularly, I will mention, of course, Alberta Directive 60, the BC greenhouse gas reporting program. Those two regulations are very detailed, very strict. They go into a lot of detail with the data requirements. So that's what we have here. Like I said, methane emissions in general from oil and gas have been identified as one of the lowest cost opportunities to reduce greenhouse gas effects.
And outside Alberta and Canada, what can you comment? What have you seen in terms of methane regulations?
Yeah, I was just going to mention Canada. It appears that methane regulations are only going to get more stringent. Again, there's that proposal for the 75% reduction in methane issued by the federal government.
Which is still not right?
Exactly. We're waiting to hear, how that's going to look like.
Yeah.
The provincial equivalency agreements, all these things, we still don't know how that's going to look like, but that seems to be the trend.
Correct. And outside Canada?
Exactly. And things have been changing recently, of course, but even last year, I attended the Global Methane Forum in Europe, in Switzerland. And one of my key takeaways of those events that I've been going around learning about methane emissions in other jurisdictions, Canada is still seen, I recognized as a leader. As a leader in the area of regulations, but also how industry responds in terms of managing these emissions.
Oh, yeah.
And I think many other countries where there's significant oil and gas activity, they're just catching up. There's the European methane regulation that recently had some simplifications, but still is asking for a methane emissions intensity for anybody that's trying to export their natural gas into the European Union. So that regulation is also driving a lot of action. Big countries producing natural gas producing countries like Qatar, Kazakhstan, they are going to have to meet these regulatory requirements to access the European market. So that's driving activity.
Yeah. Now, obviously, there are lots of different ways to mitigate methane emissions. And of course, depends on what that source of emission is. Before I joined Process Ecology, you guys did that work, and we released the team platform. Any quick word on that worth sharing to this audience?
Yeah, no, that was a very interesting project we did with ECCC, Environment Climate Change Canada. The idea there was to help them evaluate, that proposal of 75% methane reductions from 2012 baseline, whether that it was even possible, technically feasible. So it was a techno-economic analysis that we did with them. Again, we developed this software platform to help us evaluated a ton of different mitigation options across the upstream oil and gas sector. Something like 350,000 individual sites, 20 different mitigation technologies, and then automating all that. Ended up evaluating around 2.5 million individual mitigation projects. In short, the summary of that report, which again it's publicly available, was that yes, it was possible to achieve 75% methane emission reduction with current technology. We found that each individual project would be relatively economic at around $20 or $15 per ton. The one remaining
carbon?
of CO2 equivalent, sorry.
Not methane.
And
of course.
of CO2 equivalent. And
Yeah.
I mean, the biggest challenge, of course, with that was that even though there were lots of, reasonable projects, to get to 75% reduction, we estimated around 150,000 or 200,000 projects that would need to be implemented to reach that goal.
Oh, yeah.
Yeah.
And the report you mentioned, that's public, right? That's
Yeah,
on the Process Ecology website.
that's right. And yeah, that's right. Again, going a little bit back to tank emissions, this project covered all sources, not
Yeah,
just tanks. Yeah.
not just tanks. Yeah, yeah. Which then kind of some of those mitigations, kind of those are simple, easy projects. Tank emission, not so easy, right? But before we talk about the mitigation, we have to talk about quantification, right? I mean, how much emissions are going up there, right? So, what is the landscape of methodologies to estimate methane emissions from tanks? Kind of what's your overview?
I think it's worth maybe going a little bit back in history to learn where we are today. I think it was 2003, a CAP issued a guidance document for inventories for greenhouse gas emissions. A year later, the API compendium for greenhouse gas calculations also was published, 2004. And even since then, there was a table, I remember, with a very clear hierarchy of different methods that you could
Mhm.
use to estimate emissions, including from tanks.
Yeah.
And again, the hierarchy was pretty much saying, if you want to get more accurate, two things. You're going to need more data, and it's going to be more expensive, right? Uh, the process simulation tools, for example, that we use in our daily activity, they were recognized back then as some of the more accurate methodologies that you could use.
Okay.
But again, they were identified as expensive approaches and also requiring expert involvement,
Okay.
at the time. Now, again, that's several years ago, and what we have seen, over these years is that especially with the advancement of digital technologies,
Yeah.
cloud, computing, web platforms, all these things, then I don't think that hierarchy applies anymore, and
Hmm.
we should all be using these more sophisticated simulation
Yeah.
methods including, I mean, of course, in our activity for regulatory reporting that we do for our clients, we built those methodologies right into our platforms to make sure that we're doing the most accurate
Yeah.
possible.
Yeah, let me jump in to
Yeah,
share a little bit of what we've been doing on the engineering front, because this year we've been quite busy with some specific modeling projects to estimate methane emissions from tanks. A little bit kind of driven by the regs in BC, which again more stringent on venting emissions from tanks. And I mean, it has been interesting because we have looked at produced water tanks, condensate tanks, sales oil tanks, condensate that stabilize, not stabilize, and different types of tanks, fixed roof, floating roof. And again, I mean, so as he was just kind of describing, right? So process simulation is the foundation for those methodologies calculations. But some people kind of look at a simulation model of tank and kind of have this false perception that's a very simple task compared to a full crude distillation unit, which is a very complex simulation model. Yeah, I see the point, but you really have to be careful and understand what you are doing. So, for example, one of the interesting projects we work on is on produced water tanks, right? So that kind of a production tank, and you have this produced water coming at high pressure, flashes off the tank, and you have that gas kind of venting off the tank. And so we had quite some learning to get it right with the simulation model. So it's not just a matter of mixing methane and water in a simple Payne Robinson fluid package in your HISA simulator. No, it's more tricky than that, right? And what kind of plant data you need? How do you calibrate that model? So my point here is yes, process simulation now it's simpler, it's cheaper, it's more accessible, but still you need quite some expertise to know how to use those models, right? And just a kind of a little bit of sharing on the produced water learning, right? Because again, the question is you need data as you kind of mentioned, right? So more
Yeah,
data, better
yeah,
the calculation. And for the produced water tank, we came up with this methodology where you take a traditional produced water sample, look at the oil and water residue in that produced water, and using that information, we can back calculate how much methane is going to vent from the tank. And the interesting thing is we had some good quality plant data, etc., which we could validate the model. And the model is bang on. I mean, it's kind of a really, really good representation, which means that with a simple, cheap water sample, you can go back, build your simulation model, and assess, estimate how much methane is venting off the tank. Yeah, so
yeah.
we've been very busy on that front.
No, and that's great, Denise. Again, all the engineering knowledge that you bring and the modeling, the simulation that we've been talking about, and where we are now, and I'll take a little bit of a parenthesis to talk about accuracy, but we can do better now with these calculations. We can start doing these things real time,
Correct.
not once a
Yeah.
month, not once a year, as the regulatory used to be. But let me just say a few words about this drive for increased accuracy, right?
Yeah.
Again, initially the regulations included some, opportunities to use correlations to report on your tank emissions, baskets, bags, standing. There's a few of those simplified correlations. But I think, as the methane detection industry and several companies started developing really good sensors, and as soon as they started deploying this across oil and gas facilities, call it satellites, drones,
Oh, yeah.
airplanes, fixed sensors. There's several of those technologies, atmospheric sensors. Then we started seeing these reports coming out of these studies showing that the emissions that they were seeing were much higher than what was being reported,
Oh, yeah.
let's say to government
Mhm.
agencies. So it's again, policymakers, even general public started thinking, well, almost concluding that, oh, look, the industry is underreporting,
Correct.
and I mean, there's a couple of ideas I have around that. But the reality is that, you cannot compare an engineering calculation that is based on an annual average with an
Mhm.
instantaneous sensor, right? That's just,
Sure.
that's meaningless.
Correct.
Uh, so anyhow, how this discrepancy still is pretty significant. So how could that be? And I have a really good example. For example, in the regulations today in Western Canada, let's suppose that you have a tank or a tank farm that has a VRU installed on it.
Mhm.
So that is a control tank, and that is immediately assigned zero emissions. Okay,
Mhm.
because these devices are there to capture all the vapors coming
Sure.
out of these tanks, so there
Yeah.
should be no emissions. And again, that worked okay for some time as a average assumption, but again, with these more detailed measurements,
Mhm.
is not good and not good enough anymore.
Mhm.
But of course, it makes sense that it's not good enough anymore, because even if the tank is equipped with a VRU, again, we know that these systems are highly dynamic, right?
Yeah.
So
Mhm.
the time dimension becomes essential in this discussion.
Yeah.
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 We cannot compare these two things, like I say, and imagine that. So what we're proposing now is to say, okay, let's do a real-time digital twin process model that is running those engineering calculations at very high frequency in that time dimension. And we're proposing that that's a better way to really understand the dynamics and the behavior of those systems. Yeah.
Okay.
So now we're able, for example, to see the pressure profiles inside the tanks, where at some point, if there's some upset in the process upstream or something like that, then the pressure may start increasing in the vapor space of that tank, and the tank is going to react by opening the relief devices to restore the pressure to a safe level. That's an emission event, right?
Yeah.
And these things are happening. So again, the fact that there's a VRU is not identical to zero emissions.
Yeah.
Yeah.
But the keyword here, you're saying that's at real time, right?
Yeah, no, that's right. Again, we've deployed this platform in several facilities.
Yeah,
We're
I'm asking
doing a few
because
more.
about 10 years ago, working for an operator, so I developed a tool to exactly do that, right? So you go to the data historian at kind of a couple of seconds, get at the data, look at the pressure, and then see when the pressure exceeds the opening of that relief device, and then do some kind of a calculations of how much methane the tank is burping to the atmosphere. But that was not real time, right? That's kind of a more for regulatory reporting. So because at the time that's the best we could do, but with all the new tools, methodologies we have nowadays, I mean, now we can move to a completely different world where real time is a realistic approach, correct? That's what I believe the direction you're going.
No, exactly, Dennis. I mean, we're seeing that one of our deployments here in Central Alberta gas plant. We've been tracking, tank and the whole facility. Really, the digital twin captures models the whole facility, and so we're able to determine those overpressure events, emissions events, are quantify the flow rates with thermodynamics, with engineering calculations, and then aggregate, out of all these events that have happened, let's say this month, these many, kilograms of methane were released, again, for control tanks. So that's been very interesting. But the other thing that I'll mention that is, and maybe just to frame this comment, of course, it's very good for all of us to get really accurate in determining the emissions from these tanks. But ultimately, I mean, that's not the goal. We need to do that because of mitigation, because we want to reduce those emissions.
Of course.
Right?
Yeah.
So without losing, that objective, the other thing we've been able to do with real time is to use those systems to identify the root causes. Right?
Oh, sure.
Because it's all great to say, oh, pressure up, device open, boom, methane. And then you say, oh, methane is coming out and you quantify, which is good. But now if we look at the data upstream of the tank, we're able to see data patterns that are telling us the root cause of those events happen. Again, in this particular facility, we're seeing frequent liquid slugs, for example, coming into the inlet separator. Then what happens is that all that liquid dumps into the tanks, and we can very clearly see that the tank is filling much faster than usual, and the VRU cannot handle that additional pressure in the vapor space. So again, the PVRV opens, right? And there you have emissions events. So now with this knowledge, we're able to say, okay, look, a couple of things you can do: adjust the controls, the control parameters in your inlet separator to try to smooth, that slug. We also talked about improved communications with the field upstream for picking schedules. Many times those are the ones that are, throwing those slugs into the facility. And again, all these strategies would result in reduced emissions from tanks. Yeah. So, yeah.
Okay. Yeah. Well, and just kind of piggybacking, because you kind of mentioned that mitigation is the goal. And so you simplify the root cause, so check the sources, and the other front is on actually execution of engineering projects, right? So you actually have to come to the plant and make changes, change the hardware, change the piping, and again, back to my side of the business here, leading the engineering projects. There's another front, another area that we have been busy looking at the kind of the conceptual design, front end feasibility study of options in terms of projects. What can we do to reduce those emissions from those tanks? Not looking at changes in operation, but actually engineering projects. And so basically, most of the projects run around the option of what we do in terms of a VRU, right? So the different styles of VRUs. It's a simple collection system, or actually the system is a compressor, which is going to
And
push
sorry,
those
Dennis,
gases. Yeah.
sorry to interrupt there, because
Yeah.
yes, the example I was talking about is a control tank. So it
Sure. Yeah.
already has a
Exactly.
VRU, but there's so many more uncontrolled tanks out there in
Yes.
the industry,
Exactly.
right?
Yeah. Yeah.
So
Yeah.
again,
So
these solutions are there available to implement at these sites, right? So
exactly.
sorry, please go
No.
ahead.
No.
So
Sure. Yeah.
what
Yeah.
options do people have?
So on uncontrolled, right? So the easiest, cheapest, a kind of a collection system, a VRU in a sense of a collection system, and sending that to flare, so kind of a replacing methane by CO2 emissions, which is still kind of a much better. But then there are other options, more sophisticated, which we had a chance to kind of a look at. So like the use of that gas as fuel gas. So we look at the entire facility, fuel gas balance, to see if there's room for that gas. Or there are some options, some people are actually doing that, to use that gas in a recip engine to generate some electricity. Again, if there's no room to accommodate that fuel gas in the system, it's not that difficult to use that for power generation. There's some options, and on the team report, I know we mentioned that, but if there's a pipeline nearby, there's always an option to look at injecting that gas into a pipeline, or an option that I haven't personally been involved in any project, but the concept of a virtual pipeline. So that's a third-party company that comes with their trailer and kind of a collect your gas, inject to their trailer, they haul away, and they kind of put that trailer in a consumer that is going to use that gas. That's a kind of another option. And
Yeah.
so basically,
And,
we run all the economics of all those options, right?
and Dennis, I just wanted to mention, recently, having conversations and projects with our colleagues at Spartan Controls, they were also identifying some emerging technologies, possibilities like catalytic oxidizers for
Okay,
handling of that
interesting.
gas.
Yeah.
There was even discussion around the data centers, right? All these are becoming, options for
Oh
handling
yeah.
the vent gas.
But I think you need way more than just the venting emissions from tanks to power the
Exactly.
data centers. I think they're more hunger for
Yeah.
energy. Yeah, yeah.
Yeah. So look, I don't know, Dennis, would you like to add anything else to your comments? I think we
Yeah, no, I
covered
think
several
we're
things
good.
here.
Yeah.
Mitigation. We talked initially about quantification, how the trends, what we see happening, how we're doing today, trying to improve the accuracy and identify the root causes, like I mentioned, for mitigation actions. Of course, the technologies and the engineering projects that we're doing to reduce those emissions. But maybe at this time, I'll send it back to Sophia. Let's just see if there's some questions from the audience.
Hi, yes. Thank you for your insights today, Alberto and Dennis. There is a Q&A box for any questions. We really encourage questions to kind of get a little bit of interaction going. But while questions come in, I will ask a couple first. Dennis, is it possible to use the real-time tool to monitor venting emissions from skim tanks?
Oh, skim tanks. Yeah, that's kind of a tricky application. Hot water with a little bit of oil supernatant. Yeah, so the answer is yes. They are our real-time tool nowadays has the methodologies to understand the produced water from skim tanks. oil content, and then estimate the emissions from those type of tanks. Yeah.
Great, thanks, Dennis. Next question I'll ask Alberto. Does the real-time approach apply to other emission sources other than just tanks?
No, thank you. I think I alluded to that earlier in my comments. So the core of this real-time platform is a model, a digital twin of the whole facility. Like I was saying, it's important for us when we're talking about tanks to make sure that we have the upstream portion of that facility to understand the root causes. But in this case, we're modeling not just the liquid portion of the plant, but also the gas portion of the plant. The refrigerant units, the compression, all the different sections, so that we can track, of course, combustion emissions, venting from tanks, like we said, venting from dehydration plants, flaring. That's something else that is tracked in real time. So again, we get a whole picture of all the facility.
Great, thanks. Dennis, here's another question. In addition to the reduction in methane reduction, in addition to methane reductions in a VRU type project, can you also quantify the reductions in GHG emissions?
Yeah, exactly, because they go side by side, as I quickly mentioned, the case of uncontrolled tanks, where you basically collect those emissions and send to flare. So we're going to replace those emissions from methane, kind of a greenhouse effect, to CO2. And of course, then we have to quantify what that emission on a CO2 basis is. But then on the other projects, like we look at some projects with control tanks, right? And then kind of instead of flaring, trying to go to a different use. So you start with GHG as a starting point, but then doing all the equivalencies and the combustion efficiencies, and we account all of that to have an accurate accounting of what the GHG emissions would be.
Yeah, so sorry, let me just, I see a question here from Patrick. Thank you, Patrick, for sending this. And I'm just going to read it. He's asking, well, I guess everybody can read it, but he's talking about value in leveraging emissions data from continuous monitoring technologies in the real-time platform. So I'm interpreting, how can we use, these continuous sensors, like atmospheric sensor data? There could be, of course, there's point sensors, there's perimeter sensors, there's different types of data streams, cameras, there's all these different types. What we've been doing recently, again, we're lucky that the central facility in Alberta, gas plant in central Alberta, is the emission testing center. So it's equipped with several of these sensors already. For now, we've been using those mostly for validation. But again, I think there's a nuance here that I like to clarify. Methane emissions from tanks, in our experience, is mostly coming from overpressure events. So again, PVRVs, thief hatches opening. However, there's always the possibility that let me just call it a true leak. So let's say that a valve is not sitting properly, the gasket is, wear and tear. So there's some smaller amounts of gas leaking from that tank. Of course, the pressure profiles that we're seeing are not as detailed to let us see those small sources. So there is room for those sensors and for LDAR activities and so on to handle those emission types. So again, I think facilities, it could be a very interesting synergy between the modeling side of the real-time platform and combining that with these continuous monitoring technologies. So anyway, Patrick, hope that's an answer for you.
I've got another question here on the chat from Amir Tagipur. Reading his question, is there any publicly available gas analysis for venting gas from uncontrolled tanks? If so, do you have any estimate of the nitrogen and oxygen content? Okay, my answer is I am not aware of any publicly available gas analysis for that venting gas. I have seen private reports from engineering studies, but not public information. Now, at the same time, going to jump into your second question here. If so, do you have any estimate of nitrogen and oxygen content? That's a good, tricky question. Yes, we do. Uh, so all you have to do is kind of make assumptions on what the composition is at the vapor space of the tank. So typically kind of go the other way around, right? So we know what kind of is flashing into that vapor space, and then kind of using Raoult's law, you know what the proportion is of oxygen versus that hydrocarbon, and of course sometimes steam in case of skim tank. The question was asked about skim tank, so we have to take account into the water temperature, how much water is in that gas phase, and then by kind of a difference, we know the remaining volume of air, and then typical air composition, we have an estimate of nitrogen and oxygen. Yeah, that's
And
my
Dennis,
take.
let me just add something there because I was kind of digging in my
Yeah.
memory here. I'm pretty sure I've seen a couple of tables that report typical compositions but it's by industry segment, I believe. So if you're upstream, if you're midstream, they use different compositions. Let me look into that. We can send you that reference. The other thing I'll say is that there's quite a few really good resources online available with information about tank emissions and all these calculations. So after the webinar, we'll be sending out an email with some of those resources that we hope are going to be useful to you.
Cool. Yeah. A few more other questions here. I'm going to publish this one, but I think you should answer that. Or I can jump in. So it says here, does the real-time approach apply to other fluids stored in tanks? For example, methanol and methanol vapor emissions. Do you want to get started here or?
Yeah, no. Thank you. That's a great question because again, there's been in our deployments today that there's been that specific interest on methane. But however, there's nothing that would stop us from implementing the calculations for methanol or other sources. Just to give an example, for example, in the dehydration plants, right now the digital twin is tracking methane coming from that vent. If there's stripping gas in that unit or if there's a gas pump, there's typically significant amount of methane. But in that same model, in that same calculation, we determine benzene emissions coming from that same source. So again, the vapor liquid equilibrium, the composition of the fluids, it can be expanded to other species, easily when the information is available. Yeah. How about you, Dennis? Any additions to that?
I think you can go. I can jump to the next question here from Chris Skrupa. What are the primary barriers to implementing technologies for tank emissions reductions, particularly for small sources like single well batteries? What is needed to overcome this barrier? So I will get the first take here. Well, I guess the main barrier is cost, right? I mean, everything costs money, especially in brownfields. Now, the other thing is for single well batteries. I think one of the concerns is the limited infrastructure you have, right? So typically you might not have a flare header system. You don't have any consumer of fuel gas. You don't have any much consumption of power, electricity. So what do you do with that emission, right? So what options do you have other than releasing them to the atmosphere? So I guess that's where the technology that Alberto mentioned, that Spartan is kind of proposing the oxidizer. That correct? The catalytic
Yeah.
oxidizer. Yeah. So I think these would be the niche applications for this type of emissions where you cannot bring a whole VRU and then what do I do with this gas, right? Then you just create more problems, right? So there are specific technologies for small applications, and but nevertheless, I mean, in the end of the day, cost is always a barrier, right?
Yeah. No, that's right. That is, and I was reminded me of a study we did because in Saskatchewan, in some areas of Saskatchewan specifically, it's that's the situation. What you see is lots and lots of small sources, highly dispersed, no infrastructure, for gas gathering, for example. So these smaller sources are somewhat stranded. What we tried, and it has promise, but depends on the region, is clustering. If you're able to gather, some of these
Mm-hmm.
smaller sources and get more interesting volumes, then the economics of the projects start to look a little bit better. But again, that's easier said than done, right? But yeah, that's a reality. I think what we found is again enclosed combustors. It's not the ideal use of the resource, but because you're destroying it. But in terms of emissions, that's probably a really good solution for these isolated small sources.
Mm-hmm.
Great. I think we have time for maybe one more question. So yeah, feel free to pick one and then we'll wrap this up.
Go for it, Roberto.
Oh man.
I'm going to jump to a quick one here because
Yeah.
I think because that's Sophia who's going to answer that. Sophia, let me publish that question. So Amir is asking if the transcripts are going to be available.
Yes, we can provide the transcripts after. Yes, no
Okay.
problem.
Now, Alberto, you pick the last one.
Yeah, okay, there's here one from Rob, and he's asking, and again, I'm hoping I'm interpreting this properly. Is there opportunity to incorporate inline continuous real-time point source metering from tank vents in the portfolio? And yeah, absolutely. I think what we're finding is depending on the age of the facility, sometimes the operator, their practices, the instrumentation could be, really good, or some areas could be really poor. And so adding additional sensors will help improve the accuracy of the models. But again, I think it really varies. We've been talking about, adding these battery-powered pressure transmitters directly in tanks. Usually, we don't find those pressure transmitters in tanks. So again, technologies are coming out that should all be helping to get better and better results as we go. So yes.
Great. Thank you so much, Alberto and Dennis, for your insights. As previously mentioned, we will be sending out an email after this webinar with some resources, some links where you'll get your key takeaways and you can learn more. And yeah, so this wraps up our webinar series for 2025. Our next webinar will be in the new year, so stay tuned for new topics and speakers. And also don't forget to follow Process Ecology on LinkedIn and subscribe to our newsletter so you keep up to date. But thank you everybody for joining us today, and we hope you have a great rest of your day.
Thank you.